Um, so this might be one of the most important lessons of the semester, because we are learning how to take the derivative of function composition, and almost every single derivative out there is the function composition, because we know how to take the basic ones using the formulas that we memorized. So if you take a look at the derivative of, let's say, sine x, you just know it's cosine x because you remember that last time. But what happens if the derivative is of sine, let's say, e to the x? Now what, right? So what is this derivative? And clearly we don't want to use the limit definition for something like that, because it will be really annoying. So what we are going to do is we are going to learn the chain rule formula, and then we are going to use it to find the derivative of function composition. But before we do that, we have to first go back into pre-calculus and review a little bit about the function composition so that you can recognize it. Because remember, when you are supposed to take the derivative, it could be basic, it could be product rule, it could be quotient rule, it could be chain rule, and then it could be any combination of them embedded one into another. So we need to first understand some of the pre-calculus and refresh that, and then after that, hopefully, chain rule would be going easier. So technically, function composition is when you plug one function into another, so f of g of x, also denoted ff, this little circle of g, and you can say of x. So function composition, when you take one function and plug into another one. So now it's not just that you need to recognize that, but you also need to be able to decompose these functions when you run into them. So example for something like this would be, let's say, f of x is equal to x squared plus 3x minus 1, and then g of x is equal to, let's say, cosine x. So how much is f of g of x? Now this means that g is plugged into f. So f provides the main structure of the function, and then g would fill in for every x. So every x, if you take a look between this over here and this over here, you see the same f. It's the same function that is on the outside, but in the first f, you have the variable populated by x, where in the second f on the bottom, instead of x, you have g of x, which is an entirely new function. So starting by looking at the structure of f, this is how I like to start. I say something is squared, then something is times 3, and then I have minus 1. I call this the skeleton of the problem, of the function. And now what goes in these parentheses? Well, the g of x goes there. And g of x is cosine, so that g of x goes in there. And since g of x is cosine, we just replace every g of x with cosine, so we get cosine squared x plus 3 cosine x minus 1. And this would be actually the answer in this case, where we are just trying to put two functions into function composition. But we can also go and say g of f of x. So what's g? It's cosine of something. And what's that something? Well, in this case, it's f of x. So now what is that f of x? It's going to be cosine of open parenthesis x squared plus 3x minus 1. And that's the answer. That's the function composition when it goes the other way. So the first answer is for the function composition f composed with g, f composed with g, which means g is the one that is plugged into f. This one, g composed with f, is that f is the one that is plugged into g. As I move the temperature from negative 40 into 50. No, at 71. So we'll see how that goes. If it starts melting, then we'll put it down to negative 30. All good with this? So now earlier I mentioned the problem that you are supposed to take the derivative of cosine e to the x. So cosine e to the x is the function composition where, what's the outer function? What's the main function? Cosine x, good. So so f of x, which is the outer function, is cosine x, and then the inner function is e to the x. So that this is f of g of x. So technically this is the skill that you are going to need to recognize what is the outer function, what is the inner function. How about x squared plus 3x minus 1? I guess that's my go-to polynomial because I had the same one previously. I'm gonna change it. Just make this 13 and then we're gonna make it plus 12, all right? Raised to the 8th power. So how do we decompose this one? What's f of x? X to the 8th, very good. And what's g of x? Yes, call that the guts. You have the skeleton and the guts. So you are learning anatomy and physiology at the same time with calculus in this class. Paid one price. But good. So now we are ready for the chain rule. I really like the name chain rule, very appropriate for what this happened, because the chain, the links, and can go on for as long as you need it. So we are addressing how to find the derivative of, let's say, cosine of 3x squared plus 1. How to find the derivative of this. So now I want to first understand that the f of x, which is the outer function, is cosine x, and then g of x, which is the inner function, is going to be 3x squared plus 1. So now what are we supposed to do? We are supposed to find the derivative. Remember that the derivative of x in respect to x is 1, and the derivative of y in respect to x is whatever it works out to be depending on the function. What happens when I introduced another function? Well, in that case, you are supposed to keep taking the derivatives for as many function compositions as you have, which means you take the derivative of the outer function, and then you dig one layer inside, you take the derivative of that, then maybe you have to go one layer inside more, and so on. So what is the definition for the chain rule? If you are looking for the derivative of function composition, you will take the derivative of the outer function with g still plugged in, and then times the derivative of the of g of x. Now this is what we call a chain, and it can go indefinitely. We are going to see a lot of stuff depend on this, later concepts of calculus as well. So it is very important to get really familiar with this quickly. Now, one way to understand this is when you plug one function into another. So if you are to write d dx of f of g of x like this, and then you say the derivative of f with the g still plugged in times the derivative of g in respect to x. This looks like f times y, but it's f of g. So let's take a look at an example, maybe the one that we just had. Cosine of 3x squared plus 1. So we are supposed to find this derivative. Well, we already know that the outer function is cosine. So what's the derivative of cosine? Negative sine x. But instead of writing x, we write 3x squared plus 1. And then we have the times. And then we have to take the derivative of g, which is plugged in, which is 6x. Very good. So that is your chain right there. That's the chain. I'm gonna get, you know these are examples. Let's find the derivative of e to the x minus x, everything raised to the 10th power. So what should I do? What should I do? What's the outside? X to the 10. So what is the derivative of it? 10x to the 9. So 10 something to the 9. Now that something is our e to the x minus x. And then the derivative of e to the x is x minus 1. That's the chain. Now what was the question / comment? We eventually did. Even chain. It's the derivative of the inside. So, I mean, again, as I said, I rarely memorize the things using, words and stuff. I associate stuff with pictures. But for whatever reason, I remember when I told you how I memorized the product rule and quotient rule? So for chain rule, I remember the derivative of the outside times the derivative of the inside. That's how because this, this e to the x minus x looks like it's in the belly of x to the 10, right? So that I call it the inside and outside. Outside is, x to the 10. It is very important to learn how to read formulas. You see, the function of the g of x, and that g of x is still plugged in for each x in f prime. So you can take the derivative on the side and then replace all the x's with the function that was originally given. Let's take a look at some of these. We'll start with vanilla problems, obviously, from homework, and then we'll work our way up. All right, so try this one on your own. Remember, the derivative of the outside times the derivative of the inside. If you're able to decompose this, you will know which one is which. So what is the outer function?
I have a question.
Yes.
Can you just simplify this before you do the square root? Can you make an x plus 3?
Can we? Let's discover together. Every time when you have some kind of algebra question like that, try some numbers and see if it works. Because the two should give you the same answer. Let me chisel this one on the board. So can we cancel square root with a square, and square root of 9 is 3? The answer right off the bat, I will tell you, it's no, and it's never possible. But let's see that it doesn't work. So I'm going to write the original problem, square root of x squared plus 9, and I'm going to try this on some random value. So let's compute this at x equals to, I don't know, doesn't matter, 10, whatever. Doesn't really matter what you pick. Pick some number. So if you compute this at 10, you get the square root of 109. Because 10 squared is 100 plus 9 is 109. There is no square root of 109 as a whole number. There's going to be a whole bunch of decimals there. But let's keep it there. And now I'm going to simplify this into, well, it's not going to be correct, but I'm going to write it as x plus 3 and compute also at x equals 10. It has to give you the same answer. Otherwise, it's not good. So this is 13. Now I know that 13 squared is 169, and this is not 169, it's 109, which means that two expressions are not equivalent. If you have something that cancels, when you compute it in a non-canceled form and in a canceled form, it always gives the same value on the other end. So, I don't know, x minus 5 over x squared minus 25. If you compute this at any value you pick, it's going to be the same as if you computed it at 1 over x plus 5. So these two will always produce the same value for the same x because this is the canceled version of that, where these produce different values because they are not. So anytime when you have some kind of algebra question, especially you're sitting on a test, right, you can go into the margin or to the empty page on the test and then just run that calculation quickly. Now don't use only one number, because if I picked 0 over here, it would work, and you might be led to believe that it's okay. This 0 is just square root of 9, which is 3, and 0 plus 3 is 3. So that's the one misleading value that could make you believe that this actually works. So that's why I compute 2, 3, 4 values just to be sure, and then you know, since you're not getting these to be the same all the time, you know that that cancellation is illegal. Yeah. So the outer function is square root of x, which is x to the 1/2. So we can rewrite this as the derivative of, open parenthesis, x squared plus 9 raised to the 1/2. So bring down 1/2 of something to negative 1/2, because we know when we take the derivative, it's minus 1 on the exponent. 1/2 minus 1 is negative 1/2. And then we write the guts, right, which is x squared plus 9. And then times 2x, which is the derivative of the inside. So it's the derivative of the outside times the derivative of the inside. Clearly 2 and 2 will cancel, but 1/2, right? And we are left with x, x over square root of x squared plus 9. That's it. That's the derivative. Questions, concerns, anything? So you're either understanding this or you're completely lost.
So with this, like, how do we know when we're supposed to be taking the chain rule and when you can just take a derivative or something?
Well, taking just the derivative, that means that you're looking at the basic function. The chain rule is for compositional functions.
Oh, okay.
So none of these are, right? So if you're looking at the chain rule is here because you have 1/2 exponent of this. If it was just x to 1/2, it's a basic derivative.
Yeah, so I can just take that out.
Because it's a mess, right? It's a mess, then it's a two-step procedure. Derivative of the outside times the derivative of the inside, which is that. What I found throughout, doing this for over 100 years, is that you guys tend to confuse the product rule with the chain rule, and that's something that we really have to address. They are not even close, but you see that the problem over here, we started with sine e to the x. It can't be a product rule because the sine has the e to the x as its argument. So you cannot separate. If you separate these two, then this is a religious term, has nothing to do with mathematics. It has to be followed by an angle or a function or something in order for it to be mathematics term. So you cannot put multiplication in between because then this has no argument, and then it's no longer math. So we have to be careful about that and distinguish when do we get to use. So if this was sine x and then e to the x, yeah, that's a product rule. But because there's no sine x, the sine of this, that means that this one is plugged into sine. And as soon as you have nested functions, you will have chain rule to work out. Yes?
I mean, is it safe to say the most common ones are when functions are inside trig functions and when functions are inside exponential?
Yes, and ln.
Okay.
But then you are also going to have polynomials, so technically all of them. And any combination, I mean, you can have sine x in parentheses raised to e to the x, right? So they can go either way. We might not have the application, but the beauty of math is you can put together anything, and if it matches some application, it's awesome. Mathematics is extremely, extremely broad. It's in the base of every other science out there. So if you take a look at, let's see, what should I? Well, let's just take a look at, sine x e to the x versus sine e to the x, right? You see that the argument of sine is e to the x here, where over here sine has x as the argument, and then times completely different functions. So that's a product rule, that's a chain rule. That's the major difference. Now, as you said, mainly trig, mainly this, mainly that, I can put all of them in one problem. And we'll see that this actually can string as far as not just two functions. You can do the function composition of 5 of them, and then you just go 5 chains. That's something that we're going to take care of soon. Okay, let's take a look at another example from the textbook, and then we'll do more examples after that. Now, what can I do? You signed up for a class. Could have had summer off, but yeah, I know. Actually, I don't. I never did it. So the problem from the textbook 28 says, what is the derivative of e to the tangent x? It's okay, they're gone.
What?
They're gone, don't worry about it.
It's a break, too much.
Cool, perfect timing, right? It's not raised, it's raised to the tangent.
No, like what's on the outside, that's masking like what's there.
Nothing. There's no there. See to the.
I can follow the pattern of from before it.
Oh, because C to DX, C to DX tends to be evil. Because the derivative of itself.
Okay. So if you were comps, then there might not be. Wouldn't say that though.
Yeah.
Alright.
The exponent will become the sine. So revisit that. 1.3 equals to the common one.
No, I don't know. Oh, really? They won't do anything yet?
Not how.
I didn't take it yet.
Which? Different levels of human memory and said model will not transfer depending on which memory transfer to visual memory. So looking into
Minus transfer.
so some of the which is very interesting because you're transferring from a school into a school with the same major, and then same math department that accepts it, so one major belongs to the other. As a transfer, which is that's why you have to make sure that all calculus transfers everywhere in class because you have one of the toughest calculus curriculums in the gravity because you have to make sure that our students transfer from IT and space and go on everything and GXP. So a lot of students from universities get burned on those, going forms and know, breaks loose, so he's like, what the hell, man, this is worse than Russian. Of course, so this is the MIT course if you want. So yeah, welcome. Sit right here. Would you like coffee? Would you like coffee with your change room? You might need one.
Well, that's yeah. Oh, I guarantee this course is easier at Rutgers than here. It's easier.
That's why I don't want to take it over there.
Plus, they curve, but then it's 4 times more expensive. So,
That's the only.
so you have four runs here for one over there.
Well, thanks for telling me that, and now I regret deferring. But, whatever.
What do you mean referred?
Well, because I deferred because I thought that, like, okay, math is going to be really hard there, and I'm bad at math, so I was like, alright, I'll just wait, and I deferred, and now I'm like,
Should never
I
cover
deferred.
I don't think I will.
It's not. It's not hard. It's just more expensive. It's how it goes. I remember transferring. So, this is my sad story for linear algebra. This is about 107 years ago, when I was a student here at RVCC. I took a course called linear algebra, which you can take after calculus 2, and I took it after calc 3 actually. And transferring into Montclair State, at that time, RVCC linear algebra was 3 credits, and most of the linear algebras everywhere else were 4 credits. So as I was transferring the course, they said that I have 2 options. One is not transfer it at all and take the entire course and pay for it. Well, I didn't pay for anything. And or just transfer 3 credits and then take 1 credit difference, which means still go to class every day, still take all of the tests and the final and everything like a regular class. I go with all other students, except everyone will be earning 4 credits and I'll be earning 1, and they would charge my account for 1 credit. So I said, well, I didn't care because I was on a full scholarship, so I didn't see any difference. So I said, yeah, I'm going to do the 1 credit difference because it really didn't make difference money-wise or whatever. So I go to the first class, I get the syllabus. Their 4 credit course covered less material than our 3 credit course at RV. And I was like, what the hell? We had like 1 chapter of material more, the whole chapter more than what they had. It's the same time frame, 14 weeks, right? And all of that. Plus, we had more advanced textbook than what they had over there. So with that stuff, I go, as a now alumni to RVCC. I go to the med department chair. I bring the syllabus, and I had the syllabus from RVCC. I put one, I put the other, and I just say, "What the hell?" Right? She looks at it and she goes, "Yeah, what the hell?" And then within a year, RVCC one was 4 credits. Now, see, the trick is that the linear algebra is the only course that is regarded as a non-elementary math course that we have at RVCC, because elementary mathematics is including differential equations. So that's when the elementary math is done. After that, starting with linear algebra, it's the first non-elementary math course that is considered by, IT schools. So, NGIT, MIT, and so on. So the linear algebra is usually a 300 level course, and we are somehow, which is awesome, having it as a 200, and it's transferable everywhere because we do have a very good and strong course in linear algebra. We're still 4 times cheaper, at least 4 times cheaper per credit than anywhere else. So that's why we have summers that are booming with visiting students from different institutions. So usually about 70% of classes, math classes, are visiting students in the summer, and then 30 are in-house people. So.
It's like almost all of the summer courses are like math. If you look at the available, well, most of them, like all the math classes are available
But the reason is that the math, see, the state math, it's the issue of education. It's not, we have to have them, and students must take them. Those students that really want to push, because the state legislation and all of the, you know, what Department of Education is just pathetic, because the state standard for math is Algebra 1. That's the standard. Where everywhere else in the world, Calculus 1 is. So if you are in high school, called high school, right? High school. High school, and you are graduating high school, your exit exam must be Calc 1. That's it. So going here, you are talking Algebra 2, Pre-Calc 1, Pre-Calc 2, Calc 1. That's 4 semesters, at least 4 semesters of math. You can push that into, let's say, a solid 2 years. So a student who comes in here and fails the test for Algebra 1, then that student will have Algebra 1, which is elementary algebra, intermediate algebra, Pre-Calc 1, Pre-Calc 2, Calc 1, and that student caught up with high school level of someone who took it in Shanghai, let's say, or I don't know, Germany or whatever, because that is the standard. Because of that issue, that's why. So all of the other students will be, you know, over the summer going, right? Where in US, here we are, right, catching up on that stuff. This is technically still a high school course, and it is like that. The education is deteriorating on a constant level. You know, it looks like that, you know, all of the instructors are busy with is trying to find more interactive ways for students to get more involved with the class and learn more, with students having less time and more distractions. So that's the part, plus adding the cost on top of everything. Education is insanely expensive, and that's just because the government doesn't give a crap about it. That's the reason. Where I come from, education is free. All levels, everything. But you have to place. You have to be good, and you want to have education. That is the trick. In US, people believe that if you have a heartbeat, maintain your body temperature roughly in 90s, go for calculus, it's okay. We'll see how it works, right? And if you don't place there, we can start again from, you know, saying what is a fraction? Okay. Now how do you translate? Okay. Now let's take a look at some algebra, and then sharpen the pencil, it's calculus. It is not, I know, but it's not done that way anywhere else other than US, and that's the reason why it doesn't work so well.
And it's even on the school level, so it's like high school, we spend most of its money on
Oh yeah, that's the only reason why I'm not giving money to NGIT as alumni. I started when I graduated, got the job, joined Rotary and all of this stuff, and I said, okay, so as a proud alumni, you wanna put some money in there. You see, the school is in deficit. I don't remember exactly. I believe they were like 7 million in deficit or something like that, and they were burning about 3 million a year on sports, getting nowhere.
Division 3, and like nobody plays sports there at all.
Yeah.
Basketball's D1, it's also the longest losing streak.
So yeah, so I just said, you know what? I'm gonna pull the funding until they get the president who says, all right, it's NGIT. I want to see your national sports should be like the school sports should be these two things, these two categories. Building robots, right? That's one division for sports at NGIT. Oh, actually, then there will be 3. Yeah, that's good. Chess, all right. That's one sports for NGIT. And then you have robots, number 2.
And have you seen BattleBots?
And then, yeah, that's one. Yeah, and maybe video games. That's it. Those are the 3 sports for NGIT population. It's like, soccer, really? Really? Anyway. Yeah, education is unfortunately deteriorating, and it's it's not looking better, it's looking worse. Every year, the students are weaker coming out of high schools, weaker and weaker and weaker. And we are trying to find more interesting ways to make this stuff interesting and relevant, where the rest of the world is doing things differently. Yeah?
I probably not for her this whole discussion about what is the rest of the world doing differently.
Well, education is work, education has value. Over here, there's a lot of money lying around, and you have all of these, big people on the TV showing us how it's done. So how's life done, Kardashians, right? Like collective IQ of 7. But they're good in business, so yeah, there you go. It's we should all strive, right? Oh wow.
How did you come here? Why did you come to the U.S. then?
Well, see, that's a good higher education in U.S. turned out well. Higher education in U.S. is still better than in the most. I was talking about the prep schools. So RVCC is a school where we have amazing programs, and as I said, our calculus sequence is stronger and harder than Rutgers or NGIT or technically any one of these schools because of the thorough program and no curving and all of that. Your Rutgers, they tell you that A starts at 88, and then if the whole class does 73, then that becomes new A. Right? It's a different one. We can't do that because we have transfer agreements. So it's more rigorous, and the curriculum and what we cover is right. Now, when you look at the well, I come from country that actually had an extremely strong university system, which actually fell apart due to political crisis. So I started as a student, the war broke out, and then I had to leave. So my choices were to stay with the high school, work as a technician over there, because university just fell apart. 73 professors were fired on a political basis, and they all found a job within a week elsewhere in Europe. So they just moved, and yep. So there was nothing for me in terms of education that I could have achieved. So I was presented with a choice between Germany and US, and I moved here. But it's not a choice for many people. And interesting, I mean, in my calculus one class the last fall, there was one guy from where I am, well, not from Serbia, but from Kosovo, which is part of Serbia, but he is Albanian. And it was his first semester at RVCC, placed into Calculus 1. And I started talking about it at 2 classes, and then he knew where I was from, and I knew where he is from. He goes like, the hell, I learned all of this stuff in high school, why am I here? Right? And he's looking a little bit weird at the curriculum, trying to figure out what's the, but he's still practicing English and so on. So it's a standard. It's much different. Great thing about US is that you can, layer of opportunities, and you can actually pick up whatever you left off, and then you always have the second chance and the third chance, and you can keep pushing. Where I come from, you have one chance. That's it. One chance in life through education. And if you don't make the cut, tough luck. We're not going to import anyone to do landscaping and dishwashing. That's it. You're stuck with it. So it's really competitive, and so you are going to find students here that are very, very advanced, very advanced. I actually work with 4 students from RVCC. We are working on a fusion reactor. So you have students like that. We worked on autonomous car, which is really cutting edge technology. We have students like that at RVCC, but we also have those that are taking the pre-algebra course for 7 times and still not getting through. Not because they can't, just don't care. And that's another thing. So why push through education if you right, if you don't pay attention to any? I was going to school because I was interested in these things. To me, I wanted to know how the world works, and I understand the world much better through these things. Now, you might have different ways of thinking about this. That's in my case like that. So that's why I look at the e to the tangent of x and I say, how do I break it apart? Like e to the tangent of x. If this was e to the x, the solution would just be e to the x, and I'm done, right? But it's e to the tangent of x. And then you go and you look and you say, all right, so if I am to plug in the number for x, what is the first thing that I would have to compute? That's the inner function. And then the result of that one will be computed for the second time in the outer function. So if I choose, let's say, x to be 0, then tangent of 0 is to be calculated first, which means that's the inner function, so g of x. And then once I get the tangent of 0 is 0, then I have e to the 0, which means now I'm computing e. And that's the outer function, so that's f of x. So f of x is e to the x. And g of x, the one that it's plugged in, is tangent x. And it's this tangent x that replaces this x to become e to the x. So once I have all of that, I go and say the derivative of e to the x, so the derivative of e to the x is e to the x, which means it remains the same, e to the tangent x, and then times the derivative of tangent is secant squared x. So this part is the derivative of the outer with the g still plugged in, intact, and this part is just the derivative of g, which is our formula multiplied in between. So that was a problem 28 in the textbook. We can. Why, are you disappointed? That's it. No, you learned. That's it. That's why we're here. Awesome. So most of the problems that you guys are going to see from today till the end of the calculus life is going to be chain rule as a derivative. Very rarely you will be taking the derivative of just x squared or e to the x or sine x. Very rarely. You are going to take the derivative of sine 5x. You're going to take the derivative of sine of e to the x. You're going to find product rule and chain rule and quotient rule everywhere. And then at some point, sometimes, as I said, rarely, you are going to take some of the basic derivatives. But then derivative of e to the x is e to the x, which is the concept we used here. So they are used on a daily basis, the basic ones, except they are used as a part of the bigger picture. So what else are we going to do here? Something that looks bad, hopefully. Let's see. How about e to the square root of x? You also can try cosine to the 8x. So what's the first e to the square root of x? The derivative, well, first, what's the outer function f of x? E to the x, very good. What's the g of x inner? Square root of x, very good. I can write that as x to 1/2, right? So the derivative of e to the x is e to the x, so e to the root x times the derivative of this is 1/2 x to the negative 1/2. So we can make it pretty. Like that. How about the one on the bottom with the cosine? What's the f of x? What's the outer function? Nope. X to the 8. We can rewrite this as cosine x to the 8th power. So outer function is x to the 8. The inner function g is.
No, you wrote the 8 as the exponent. Is that an exponent in the original, in the first one? That's an exponent to 8?
Yeah, because it's not in line with the rest, right? It's raised up. Cosine x. So then we have 8x to the 7th, but x is actually cosine x, so we plug in g there, and then the derivative of cosine is negative sine x. So you can make it pretty. Negative 8 sine x cosine to the 7x. So you get the idea. Now let's talk a little bit about the chains. Later on in the course we are going to use the Leibniz notation as well. So you might ask, if there is the, let's say, function of u, function of g of x so what's df dx equal to? Well, there is this chain which we can write as f, derivative of f in respect to g times the derivative of g in respect to x. And you see that these dg's, they cancel and you just get df dx. So this is another way to write the same thing. So essentially this one over here is the derivative in respect to x of the function composition, and on the other side you have the derivative, so f prime with g plugged in, that's what it means that it's in respect to g, and then times the derivative of g in respect to x. So these two formulas are the same formula, except they're represented with different notation. And you can see the chain over here. I'm going to erase this line, but canceling these two, you get df over dx, so you get df dx equal df dx. And that takes care of that. I'm trying to see if we can find. So mechanics of the problem, right? Once you know the formula, the problems should be easy. Can't really make it hard, but we can make it very annoying, because we can, right, plug product rule inside the chain inside the quotient, product rule inside the chain which was within the quotient, and so on. So they can be all put together. You can have nested multiple chain rules. Maybe we should start there. So starting the annoying portion of this, let's take a look. Try to unwind this. So the derivative in respect to x of 3 cosine to the 9th power of x to the 4th. Try that. Remembering that the chains will link. So I'll leave you alone for about a minute or so.
Check my computer with that speed of burning of everything.
I'm gonna go for this. that room over there is like 100 degrees.
The wrinkles kind of only be a thing.
So how many functions do we have here? How many nested functions do we have? We will clearly ignore the 3. We know the rule, right? Pick it in front. So yes, please. Shout out. How many? 3. Bueno. What are they? What's the most outer function, let's say? Or do you want to start with the most inner function?
Sure.
X to the 4th. So x to the 4th. And then what's one step in? Cosine x. Nice. And what's the outer one? 3x to the 9. Nice. Now this 3, as I said, could go in front of the derivative, so 3 doesn't have to be there if you don't want it. So that's f of x, g of x, h of x. So this is going to have now a little modified formula. If I'm supposed to find the triple like this, which is f of g of h of x, like this, it's pointless to memorize the formula. You'll see that you just keep taking the derivatives. So it's f prime with g of h plugged in intact times the derivative of g with h of x plugged in times the derivative of h. So now that means that I'm going to find the derivative of 3x to the 9, which is 27x to the 8. But then this is cosine x to the 4th here, right? Times the derivative of inside, so the next one is cosine. The derivative of cosine is negative sine with x to the 4th still plugged in. And finally, x to the 4th will have its derivative as 4x cubed.
Yeah, this guy's name chain rule.
Yeah, chain, right? So now how many links do you have for a 3-function part? You have 3 links. For 2, right? When you have only f and g, you have 2 links. When you have 3, you have 3 links, and so on. You see that this, it just gives you opportunity for really annoying problems, right? Something that might have like 15 links, right? Because there are 15 nested functions. We don't do that, but it leaves the door wide open for that possibility. This can be simplified nicely and written as 4 times 27 is 108 x cubed, and then all of this stuff put together. But let's just move to the next problem. Again, swimming in waters of slightly more annoying stuff. So how about sine cubed x divided by x squared plus 1? How about that one?
talking with the manufacturer.
Okay. Okay, I believe this is all okay.
We'll discuss it.
Well, I tried to register for Global Logic, but there's only one time I completed it.
It's close to 103.
That was.
That was the no, 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 no.
Okay. I was like, I was like, where's Global Logic?
I know I know much of it is fine. Thank you.
There is this good part as well.
So what is the method or derivative that we have to use here? As I stand like, ooh. Quotient rule, right? Great. Do it. Be careful when you have to take the derivative of the numerator. So this is the quotient rule.
It's like cosine, right? The derivative of sine. That's the function. That's what we problem. Yeah, but that's an estimate. John. Yes, go on.
Yeah.
No, I know what you're saying, but I don't want it to be a freaking chain rule in the middle.
Exactly.
I don't want it to
That's
No, I don't want to do that. Okay, you're right, but I still don't want to.
it's a bit of
One of those readers
the more you exist, the better it is.
so few times.
So if it's an S of function, f of x is not.
F of x would be like sine x, and then like the other one would
Oh, okay.
No, it doesn't work without it. If you haven't put that out, it wouldn't work. Now that you put it out, I have to do it.
All right. So we start with the quotient rule, and we unleash the chain rule when we are supposed to take the denominator of the derivative of the numerator. There we go. So quotient rule, see, experience right there. We have x squared plus 1 squared, then we copy x squared plus 1, and then derivative of the top, which is 3 sine squared x times the cosine x minus sine cubed x times 2x. So where is the chain rule? The new stuff right here. That's the piece. That's the new stuff. The rest is the good old quotient rule from 2 days ago. And now, can we simplify this a bit? Yeah. There's really not much we can do. Even if you factor out sine squared, the rest is just yeah. Yeah, well, there's nothing much we can do. Not even gonna make it prettier. Just gonna leave it there. What you could do is you can write 3 and then x squared plus 1 and then sine squared x cosine x and then minus 2x sine cubed x. But it's just rearranging terms. We are not actually factoring anything, or so trying to see if they have anything interesting in the textbook, and they do. Look at that one. 62. What is the derivative of open parenthesis 3x divided by 4x plus 2, everything to the 5th power? Good luck. What is the main derivative method? Chain rule. Quotient rule is embedded, right? You see that the whole thing is x to the 5, and then the inner function is the division, which means quotient rule. So we will start this one by 5 something to the 4th times the derivative of the inside. Does that make sense at all? So I like to, when I was a student looking at this for the first time, I used my finger to cover this thing. And I would say, oh, this is like x to the 5. Derivative of x to the 5 is 5x to the 4th, but I don't get to put x, I put the guts. Right? So I would cover this, and I would say the derivative of x to the 5 is 5x to the 4th, but then this goes there, and then just follow with the chain. Yes?
You can't stand that part when you're simplifying.
No. You want it in the most compressed form possible. Because eventually in chapter 4 we get to set this equal to 0 and solve equation. It gets more interesting as we go along. And now over here we will have our chain rule. So 4x plus 2 everything squared. And then on top we get 4x plus 2 times the derivative of the top, which is 3, minus 3x times the derivative of the bottom is 4. And now we simplify this because we can, right? So what do we have? We have 5, 3x over 4x plus 2. This one is nice. This one is nice to simplify. Plus, you might expect problems like this in chapter 4, so you might want to practice a little bit of how to simplify this. Look, you have 4x times 3, that's 12x, plus 6, minus 12x, so that just dies, over 4x plus 2 squared. And now, you see that denominator over here has the 4th power, and this denominator has 2nd power, so altogether that's the 6th power on denominator. So 4x plus 2 to the 6th power. And what's left? Well, 3 to the 4th. 3 to the 4th is 81. So we have 5 times 81x to the 4th times 6. Well, 5 times 6 is 30. And then 8 times 3, 24, so 243. And then a 0 because of 30. X to the 4th divided by 4x plus 2 to the 6th. Green? Whatever, huh?
So with the chain rule, like for the second part of the chain rule, it looks like you just like I thought you were supposed to take the derivative of the inside, but you just
That's the inside. It's a quotient rule, right?
I got it now.
Awesome. One more and then, or 2 more, or 3 more and then break, or 4 more. Or we won't break and then we come back. We're not going to do any more sections today. After this is going to be lab time for you guys to practice this. I'm telling you every next section, every next lecture, these... Oh wait, we haven't done the tangent line. Ha! So last class I told you that the main problem of our calculus here, calculus 1, is the equation of the tangent line, because tangent line has a slope that measures the rate of change, which measures change in time, which is why we want to know calculus. Tells us about position and everything else. So now you can find the tangent line and the derivative that you are supposed to workout is supposed to be one of these guys. So let's see. Problem 78 in the textbook says find the tangent line at 1, 2 for function equals to, well, y equals x times square root of 5 minus x squared. So the same procedure. Find the derivative. Once you have the derivative, plug in the point, and then you have your slope, and then use the point and the slope to find the equation of the line. That procedure never goes away. And as I said, the way you take the derivative changes in terms of basic, product rule, quotient rule, chain rule, implicit differentiation, that's tomorrow. So the way you take derivatives will change, but the tangent line procedure will always be the same, with step 1 being figure out the derivative, step 2 compute that derivative at the point, step 3 find b and you're done. This was done yesterday. Done with the tangent line? Let's talk about this problem together. So, the steps are always the same. Find the derivative, and you use whatever you must to find that derivative. Product rule, chain rule, quotient rule, combination of those, or basic derivatives, which won't happen anymore. So, what do we have? So, for the derivative, we can label that as y prime, we can label it as f prime of x, we can label it as dy, dx, we can label it at any one of these. What is the derivative equal to? Well, it's a product rule, right? You have two functions, function number one, function number two. Very good. And this guy over here, the second one, is a chain rule at the same time because the function inside the function. Excellent. So, we are going to do the product rule. Copy the first times the derivative of the second. Now I'm going to rewrite this second as 5 minus x squared to the 1/2 because it's easier to take the derivative as 1/2, and then you have 5x minus squared to the negative 1/2 times the derivative of the inside, which is negative 2x, and then we have plus the square root of 5 minus x squared times 1 because the derivative of x is 1. So now what is the actual derivative? Derivative y prime is equal to 1/2 and 2 will cancel. So you have negative x squared divided by the square root of 5 minus x squared plus square root of 5 minus x squared. Now this could be rationalized and factored further, but we don't need to because to find the slope, we're just going to compute that 1. So plug in 1, we get negative 1 divided by square root of 4 plus square root of 4, right? Because 5 minus 1 is 4. And we can compute the slope immediately. Slope of the tangent line is 1/2 plus 2, which is 5/2. Negative 1/2. That's what I said. So we have 3/2 as our slope. And we have 1, 2 as a point. So we now plug into y equal mx plus b. And you have 2 is equal to 3/2 times 1 plus b. So b is 1/2. Right? Because you need to add 1/2 to 3/2 to get 4/2, which is 2. So what's the tangent line? Tangent line at 1, 2 is y equals 3/2 x plus 1/2. Now I want to make sure, because I care, right? I want to make sure that that's good. I'm just going to fire up Mathematica, and I'm going to graph functions in the same viewing window and make sure that they intersect at the point. So we go plus from alpha query, graph x times, open parentheses, 5 minus x squared, close parenthesis, raised to the 0.5, that's the square root. And the second function is the tangent line 1.5x plus 0.5. So they should graph and they should intersect at the single point. Now this is something that you guys should be doing to make sure that your calculations are correct. So as you can see, they intersect right where they should intersect. The blue line here, the straight line, is the tangent line. The other line is the derivative, sorry, the function. And looking at 1, 2, two, right there is where they touch at a single point. So everything is great. You have the linear line to be the tangent line, and you also have it touching the function exactly where it should, at 1, 2. So that means the problem is good. One more, or you're good to go? You're not good to go? Okay, so one more. Fine. Okay, you're gonna do it on the board. Fine. All right, so we have a volunteer for the board.
I'm gonna do it.
It's right there. So just find the derivative of square root of x plus square root of x, like this.
Oh, man.
It's opportunity of a lifetime to show off your math skills, since you said you're good. So I hope you rewrote this with 1/2, because it's much easier to solve it as you rewrite it. So what's the derivative? How do we start? Derivative of the outside, so 1/2, right, exponent. 1/2 to the negative 1/2, because 1/2 minus 1 is negative 1/2. And we copy the guts. Then we take the derivative of that inside, and that's derivative of x is 1 plus, and derivative over here is another 1/2 x to the minus 1/2. It's called missed opportunity of the lifetime.
I'm gonna be really upset about not using that marker for the rest of the time. You're looking at me like I can't tell if you're serious.
I can. And that is the sign, what's happening right now. Good. All right. Another one?
I think I had enough.
My brains are sufficiently melted for today.
We still have 2 minutes till the end of the class, and then another 50 after that. So let's make it productive. Well, that's then the chain rule. Being able to decompose the function is important. Being able to see how many functions you have, it's important. So you have enough appropriate amount of chain rules, and making sure that the chain rule can be combined with all other rules. You can have nested chain rules. You can have a mixed with product rule, quotient rule, and then very important problem of the tangent line. So you have to find the derivative of tangent line. And that ends the section on chain rule. Stream is off, and then let's do the lab for the